Hi, this is Bruce, Amateur Radio VE9 QRP, and I'd like to introduce my satellite tracking project called qrpTracker. It's based on the Arduino suite of tools, and specifically the Atmel ATmega 328 microcontroller. With this $4 piece of silicon and a few friends, it's possible to track a dozen or so satellites in real time with excellent accuracy, and have lots of code space left over for controlling radios, running displays, or whatever interests you. qrpTracker is a hobbyist launching off point. If you want a complete tracking solution, take a look at Howard Long's excellent LVB tracker. Satellite enthusiasts might have heard of Arduino and not know what it is. Let's start with the hardware. This comes in a variety of sizes and functions, but what they all have in common is an ATmega processor with a small bootloader that makes it possible to program the processor through a serial or USB connection. Some of us like to just pop a bootloaded ATmega on a breadboard like this. On the software side, Arduino is a cross-platform programming environment that compiles your code into ATmega software and loads it into the processor. The programming language is C, but the environment simplifies some of the details for you. With the $4 ATmega 328, you get 32K of programming space and a K of EEPROM in which to store values. And this is more than enough to do some interesting satellite-related programming. For instance, here's the venerable predict program running on Mac OS, and I'm going to launch an emulation of this that's running entirely on the Arduino. You'll notice that the Arduino version includes calculations of the Doppler shifted uplink and downlink frequencies, but beyond this, that the values for azimuth and elevation, satellite latitude and longitude are the same, though the predict does longitude west and the Arduino does it east. Finally, you can read on the third line how many milliseconds it takes for the Arduino to calculate the information for each satellite. It can do it in about 10 milliseconds, so this is enough to process probably 100 satellites in a second. You probably don't want to cut and paste these calculations into every satellite-related program, so they're encapsulated in a library file using the Plan13 algorithm. qrpTracker stores Keplerian elements in a format that allows about 12 sets of elements with an associated mode line to fit in the chip's 1K EEPROM. Since 23K outboard EEPROM memory chips are only a couple of dollars, it wouldn't be much of a stretch to keep hundreds of these around. I've provided a simple C program for Unix and Mac OS that processes two-line elements and Doppler SQF files from SATPC32 and generates an appropriately sized binary and communicates with the Arduino. So we've just installed a different set of TLEs, and now we're going to run them on the predict lookalike demo. I'm copying here a date value to seed the demo. You can also use a real-time clock. I just fried mine just before I did this demo, so I'm using this hack to start the time. And you can see that new satellites are now being run through the demo because they're the new satellite values that are in the EEPROM. So some of the future things I want to do with this is to make a standalone tracking solution for portable radios like the FT817. I've written Arduino libraries to communicate with that radio and generate Morse code for user feedback. But what I'm really excited about is just how small and low power these chips can be. The tiny 0.8 millimeter version of this could be put on board a satellite so that the bird itself could work out where it is and change its transmissions or modes accordingly. Well, that's it for this demo. If you're interested in documentation or code, please check the website that you see on the screen or go to my blog at ve9qrp.blogspot.com. 73.